All right, so yesterday we finished up talking about significant figures and all the rules associated with determining significant figures and then doing math with significant figures. And the first rule we said was that anytime you have a non-zero number, it's significant. Anytime you have a zero between non-zero numbers, it's significant. Anytime you have a zero to the right of a decimal point, it's significant. And then anytime you've got a zero left of a decimal in a number greater than 10, that will also be considered significant. So let's go through and do a couple more examples just for warm-up. All right. So let's do this example. So let's say I've got 40 milliliters, specifically 40.0 milliliters of a solution, and I want to figure out how many grams of that solution I have. First of all, we would need to cancel out milliliters. So we'd put milliliters on the bottom, and we'd put grams on top. What sort of conversion would this be? How do we relate grams to milliliters? It's something we did in lab. When we have the units grams over milliliters, it's referring to something very special. Density, right? So we're using density conversion here. So we can convert between milliliters and grams by using density conversion. And for this specific example, the density of my solution is 1.562 grams per milliliter. So I looked it up. If we go through, we can cancel out milliliters and milliliters, and then we should be able to do our final answer, but we need to keep track of Sig Figs here. So how many Sig Figs should our final answer have? What do you guys think? 3, right? So if we look at this number right here, we've got 3 Sig Figs. And if we look up here, we've got 4 Sig Figs. So we need to keep track of this and always, in the case of multiplication or division, stick with your fewest number of significant digits. So if you do the math, whoop, just 1 second. Sorry, technical problem here. There we go. If you do the math, you get 62.48 grams, which means our final answer should be what? 62.5. Yeah, 62.5. We need to round in this case. So because of this 8 over here, we want to round the 4 that's next to it up to a 5. So we'll do 62.5 grams. Make sure that you really pay attention to Sig Figs on homework and exams because I'm kind of a stickler for it, and your instructors in the future might be as well. All right, let's do one more warm-up example. Let's say I've got 3 kilograms, and I want to go to grams. What would we need to do to convert from 3 kilograms to grams? What was that? Yeah, cancel out kilograms. And how would we do that? So we've got 3 kilograms. We'll put kilograms on the bottom. Grams would go on top. And what number goes where? 1,000 on the top. So in this case, remember that there are 1,000 grams in 1 kilogram. And if we go through and we do this, we can say that this would be 3,000 grams, but it would not be correct to say 3,000.0 grams, right? Because in this case, how many sig figs do we have in our final answer here? Remember, we only count the zeros to the left of a decimal point. In this case, there's no decimal point. It would just be 1. So we have 1 sig fig here, and we've got 1 sig fig here. So our sig fig should match. If we were to look at this one, how many sig figs would be in that answer? It would actually be 5, right? Because when we have a decimal, we count even the zeros to the right of the decimal point. So in this case, it wouldn't have this because there would be way too many decimals. It looks exactly the same to us, but that decimal point makes a really big difference. Another way we could write this would be to do scientific notation, which would be 3 times 10 to the what? If we wanted to write 3,000 in scientific notation. 10 to the third. So we can imagine this invisible decimal point going 1, 2, 3. So we moved it over 3 spots. We would say that would be 10 to the third. So either of these answers would be acceptable because they both have one significant figure in them, right? So in the scientific notation, we only have one significant figure. The 10 to the whatever power doesn't get counted when we're looking at sig figs. Oops. Oops. Sorry, guys. All right. Does that make sense with sig figs? The other thing, too, that gets confusing for people is, do we count sig figs for this conversion? For 1,000 grams to 1 kilogram? No, we only use significant figures when we're measuring something. If it's defined, meaning like 12 eggs in 1 dozen, you don't need to include sig figs or worry about sig figs in that case. You only worry about sig figs with units that are measured. So this one is defined, not measured. So we don't count sig figs. All right, so let's continue on a little bit too and talk about accuracy when we're measuring versus precision when we're measuring. And these are really important terms in science, but people mix them up all the time. So what does it mean when you're accurate? You can think about it. What's that? Yeah, exactly. So imagine it this way. If you're an accurate dart thrower, you're going to hit close to the center of the board, right? You're not going to hit off the board. So accurate really means that you're close to the correct value. Specifically, your average is close to the correct value. This is different than precision. Precision doesn't mean that you're close to the correct value, but it means that all of your data points or all of your shots are really close to one another. So what I call this is a tight cluster of data. And I like explaining this using the dartboard analogy because I think it's one of the clearest ones. So let's draw 2 different dartboards. You can see my artistry here. Let's say I'm a dart thrower and I throw darts in each of these 4 spots on the left. Is that accurate or precise or both? So the average is actually fairly close to the center. If we were to average all 4 of these points, it would kind of bounce out to be close to the bullseye. But it's not very precise. It's not a tight cluster of data around the bullseye. So what we'd say is that this is accurate, but not precise. And then conversely, I could have a dart player that throws 4 darts over there. And what would this be? It'd be precise, but not very accurate, because if you take the average of them, it's way off the correct value. And then last but not least, we could have our last bullseye with our expert dart thrower. And it's all clustered in the center. And in this case, we could say that this is precise and accurate. So these are terms that get thrown around a lot and kind of misused. A lot of people think that precise means accurate, but not exactly. Precise just means that your data cluster is really close to one another. Accuracy is something that's a little bit harder to measure unless you get a lot of data involved. Does that make sense? All right, let's do some practice questions before we go on to the next chapter. And what these are similar questions to what you might see on a quiz or an exam for this class. So let's do the first one. A key aspect of a scientific hypothesis is that it must be creative, unique, testable, persuasive, or understandable. What was that? Testable? Yeah, exactly. So having a creative hypothesis, yeah, that's great, but you have to be able to test it. Unless it's testable, it's just your opinion, right? So in this case, your hypothesis must always be testable. All right, let's do the next one. Which of the following processes represents a chemical change? Water freezing into ice, water evaporating, butter melting in a hot pan, or a bicycle that's left outdoors beginning to rust, or sugar dissolving in hot coffee. So I heard a few D's. Why do you guys think D is the right answer? Yeah, exactly. So in this case, the bicycle might have iron in it. The iron reacts with air to form rust. So we're actually changing the material of the bike, right? When water freezes into ice, it's still water. It's just in a different form. Same with water evaporating. Same with butter melting and sugar dissolving in coffee. So in this case, this would be the best answer. All right. What quantity represents the smallest mass? This one's a little trickier. So I'll give you guys a minute to work on this, but one trick I might do is try to convert them all to the standard unit, which in this case is grams, and then compare them. Otherwise, it can be more difficult to. So I'll give you guys a minute too, but try to convert all of these units to grams. I'll give you guys a hint with the first one. We want to cancel out kilograms, so we'll put that on the bottom. We want grams on top. There's 1,000 grams in 1 kilogram, which means that we should have 10 grams, right? If we go to the next one, this is pretty easy. It's already in grams, so we'd say 1.0 grams. What about 100 milligrams? How many grams would that be? Yeah, 0.1. So if we go through and we do the math, we want to cancel out milligrams. There are 1,000 milligrams in 1 gram, which means that this would be 0.1 grams. And then let's do this one down here. 1,000 milligrams would be 10 times that, so that would be 1.0 grams. And then 100,000 milligrams would be 100 grams. So based on this, which one's the smallest unit? C, yeah. So if you ever are stuck on a problem like this, try to convert them all to the same unit. Otherwise, it can be pretty tricky to determine which one's the largest or smallest number. All right. Let's do the next one. A 10-gram sample of which of the following substances would have the greatest volume? So let's think about this just theoretically. If you're really, really dense, do you take up much volume? No, but if your density is really low, that means you take up a lot of volume. So in this case, which one would take up the most volume? Hexane in this case, because if we look at it, its density right there is actually the smallest value. The more dense something is, the smaller the space it takes up. So in this case, hexane, which has the lowest density, takes up the greatest volume, excuse me. Which one would take up the least amount of volume? Which one? Yeah, copper. Because copper is very, very dense, that means it's very compact. It doesn't take up very much volume at all. So that one would take up the least amount of volume. All right. This is a good one. The energy required to heat 1 liter of water from room temperature to boiling is... I'll give you guys a minute to try to work on this, but I'll give you guys a hint that might help. What's the temp change? What do you guys think? Yeah, the boiling point of water based on our SI units is 100 degrees. We're going from 20 degrees to 100 degrees, which means our temperature change is going to be 80 degrees Celsius. And then we said before that 1 calorie is the heat required to raise 1 gram of water by 1 degree Celsius. So we've got a few things we know, but this one's a fairly tricky problem to work through. So what do you guys think we should start with? Yeah, we should probably change liters to grams, because if we look at our calorie definition, we're referring to grams in here, right? So we've got 1.0 liters. We want to cancel out liters first. And what should we maybe convert it to? Yeah, probably milliliters. So we've got 1,000 milliliters in 1 liter. And then how can we convert from milliliters to grams? What do you guys think? We have that special conversion factor. Is related to lab. How can we relate mass and volume? Yeah, density, right? So in this case, density is a relationship of milliliters to grams or grams to milliliters. So we can go through and we can cancel out liters and milliliters. And then the density of water is defined as what? It's just 1 gram per milliliter. It's pretty easy to remember. So we've got 1.0 grams per 1 milliliter. Okay. And then what we can do is we can now use the calorie conversion. And we can say that 1 calorie is the same thing as heating 1 gram of water by 1 degree Celsius. And we know in this case that we're raising it by 80 degrees Celsius. So just like with our normal unit conversions, we can cancel out grams and grams, degrees Celsius and degrees Celsius. And if we go through and we do all the math, we get 80,000 calories. Or another way of writing this would be 80 what? Or 80 kcals. So either of these would be our correct answer. So if we go back up and we look at this one, the correct answer would be B. So this one would be a particularly challenging problem if I were to give it to you on the exam. But I would try to give you information like the definition of a calorie is the temperature or the heat required to raise 1 gram of water by 1 degree Celsius. Does that make sense? It's a lot of unit conversions in this class. All right. Which of the following claims are falsifiable? A classmate claims that carrying an amethyst crystal will increase your mental alertness. Or your fellow student claims to have memorized all of the element names and symbols on the periodic table. Or a self-help guru claims that if your desire for success is strong enough, you will receive it. Or an alternative health practitioner claims that drinking energized water will promote cell health and increase moisture absorption by your body, resulting in increased vitality and overall energy. Which one is falsifiable? Can we really come up with some sort of metric for success? Maybe. It depends if you want to put like a grade or monetary value on it or something like that. But success is really hard to define across multiple people. So I'd say probably B would be the best one. Because what you could easily do is if one of your friends says that they've memorized all of the periodic table, you could say, oh yeah, what's Hg? And maybe they would get it wrong. So you could quiz them and get a definite yes or no answer as to whether or not they actually have the entire periodic table memorized. All of the other ones are kind of up to an opinion, right? If it's an opinion, that's not something that can be easily falsified. All right, let's do some of these questions that I've pulled up too. What state of matter doesn't have a definite volume or shape? What do you guys think? Would it be a solid, a liquid, or a gas? A gas, right? So a gas will take up the volume of whatever room it's in, right? So in this case, gas would be the most appropriate answer here. All right, question 2 is, which of the following is a mixture? And I've got copper in there twice on accident. Copper, or silver, or soda water. So what is a mixture by definition? It's 2 or more things, right? Copper, if we look at the periodic table, is number 29, that's Cu. So this will be an element. Silver is Ag, so that's number 47, so that's an element too. Soda water is a mixture of water and what? And carbon dioxide, right? So when you buy carbonated water, it actually has dissolved carbon dioxide in it. So in this case, soda water would be a mixture of water and carbon dioxide. Some of you guys might have a soda stream and you have to buy those CO2 cartridges to attach into it. That's so you can mix your carbon dioxide with your water. All right, which of the following is not an element? Aluminum, brass, lead, or sulfur? So let's look at the periodic table. So we've got aluminum, Al is number 13. Brass, some people would say B, but B is actually boron. So brass isn't on there. But let's check the other ones just to make sure. We've got lead, which is Pb, which is kind of weird. Does anybody know why lead is called Pb? Trivia fact. So the Romans used to use lead as their plumbing system. Has anybody heard about the Romans going crazy from lead poisoning? Yeah, they got a lot of serious lead toxicity from their plumbing. But the original way they named lead was plumbum, which is short for plumbing. So it gets this Pb symbol. So lead is actually Pb on the periodic table. And then sulfur is up here, and that's S. So out of all of these, we've got lead, sulfur, and aluminum on the periodic table, but brass is not. Brass is a mixture of a few different metals. Specifically, I believe it's copper and tin. And you can vary the ratios on it and get a nice metal that's a lot stronger than each of the individual metals. All right, a compound can be separated into its elements by what? Can we physically break apart a molecule or a compound? No, we can't take scissors and cut water, right? So it's definitely not going to be physical. Mechanical, can we rip apart water? No. Can we magnetize things and rip them apart and actually break bonds? No, at least not currently. So the correct answer for this one would be chemical. We can chemically break up molecules and compounds, but it's very, very hard to do it using physical means. It actually, there was a research group, I think 2 years ago, that claimed to have done the first ever physical breaking of a compound. And all the chemists in the world sat there and kind of scratched their head trying to figure out what was going on. It turned out that one of his research students made up all of the data, so he had to go back and retract 15 papers trying to claim that he was the first one to do this. Kind of embarrassing. All right, the smallest part of an element is an what? An atom. So we said an atom is the basic building block of all matter. Mass is just a measurement of how much it weighs, more or less. A molecule consists of multiple atoms, and a neuron is a part of your brain, so that doesn't make any sense. All right, what is the chemical symbol for potassium? This is another tricky one. It's K. A lot of people get confused and they immediately jump to the letter that matches it, and so they say P. What does P stand for? Actually, phosphorus. So don't take the periodic table at face value and think that it should match up with the English language term. Oftentimes it doesn't. It goes back to Latin roots oftentimes. So in this case, the symbol for potassium on the periodic table is K. And if we look at its number, it's number 19 on that far left side. So let me even add that in there. So one thing I would recommend doing is anytime you're working through homework problems, always have your periodic table open and then double check, because it's very easy to get confused with some of these. That goes along with number 7. Hg is a chemical symbol for what? Yeah, mercury. So in this case, it's one of those chemical symbols that doesn't make a whole lot of sense in terms of English language, but hydrogen is H. Magnesium is Mg. And kryptonite is what is bad for Superman. So that doesn't make much sense. So mercury is going to be Hg for this example. One thing I will say too is the periodic table that I give you guys on the test doesn't have the names on it. But what I will do during exams is give you personalized periodic tables too. I still want you guys to be able to predict what the chemical symbols and names are as quickly as possible. But if you get stuck on them, I'll give you guys a little bit of help on that. Sound good? All right, let's switch to talking about atoms in the periodic table now. And this is chapter 2. So let's do our lead-in question of what is an atom? We already said that it's the smallest unit of matter. And I think the interesting part about an atom is that we really can't easily split it into smaller pieces. Does anybody know the exception to this rule for splitting an atom? World War II? Yeah, the atom bomb is a good example of this rule actually being violated. With some of the really heavy atoms, like down on the bottom of the periodic table, uranium, which is 92 down here, you can actually split some isotopes of uranium and create an atomic bomb. The other weird example for this is the Large Hadron Collider. Has anybody heard of that? Basically, what they do is they take these particles and then they smash them together at super high speeds and then see what comes out of that. So that Higgs boson thing that was all over the news, kind of similar to that. They can do this using really advanced physics. But as far as we're concerned, an atom can't be broken down into smaller pieces. The weird thing is that when I was in high school, the general consensus was that atoms are really theoretical things that we can measure, but we can't see. We just have to trust that they're there. And then I saw this, and it kind of blew my mind. So I wanted to show it for you guys. So we can not only see individual atoms now, but we can actually move individual atoms now, which is fascinating. And then if you're a big tech company with a lot of money and time on your hands, you can make a movie with it. So kind of a cool example of the idea of an atom, but an atom is something that's incredibly small. For a long time we thought we couldn't see it, and now we can actually see not only individual atoms, but we can see biomolecules like DNA and proteins and things like that, and we're understanding a lot more about chemistry, arguably now, than we have at any point in human history. So chemistry isn't a science that's been entirely figured out yet. We're still arguably figuring out quite a lot as we're going along. All right, so there are some rules associated with atoms, and these are called scientific laws. And I wanted to bring up this term again. The idea of a theory versus a law. What is a theory? What do you guys think? Yeah, exactly. It's an explanation with a lot of research behind it. What about a law? Does a law explain how something works? Not really. It's more just a summary of information, right? So it's different than an explanation. It doesn't explain the nitty-gritty of why it happens. It just explains what happens. So in this case, I describe a law as a summary, but not an explanation. So the first law that we're going to talk about is a pretty simple one. It's called the conservation of mass. And this is a law. So it's not something that explains why it happens. It's just a summary of what happens. Conservation of mass says that matter cannot be created or destroyed. And it's a pretty simple thing to measure. And we actually get to do this during our next lab using a different chemical, chemical reaction. But let's take this example out of the book. If we take 100 grams of mercuric oxide and we decompose it, we will form 92.61 grams of mercury and 7.39 grams of oxygen. So you can actually weigh out that oxygen that you've collected in a balloon. But the key feature with this is that this equals the 100.00 grams that you started with, right? So you're not going to create or lose anything during this reaction. So conservation of mass is a really simple idea. But let's explain this too using a different chemical reaction now. Let's say that we do oxygen plus methane will form carbon dioxide plus water. If we go through and we would draw this out as a chemical reaction, we would say we need 2 oxygen molecules, so this would be 2, and then oxygen is O2. And then we would add this to methane, which is carbon bonded to 4 hydrogens. And then we would get carbon dioxide, which is CO2, plus 2 H2O for water. Really, all they're saying is that the mass of your starting materials regardless of whether or not they're a liquid, a solid, or a gas, is going to be exactly the same as the mass of your products. Doesn't matter if you've got 4 reagents, 5 reagents, or 1 reagent, it's going to weigh the same as the mass of your products. Alright, there's also one other law that I wanted to mention. This is called the law of defined proportions. And this one says that a compound or molecule always contains the same elements in the same ratio. And the example I already brought up to you guys was water. And with water, we said that water can be chemically written as H2O. And what this means is that there's always a 2-to-1 ratio of hydrogen to oxygen. Right, it's a defined rule. If we added on a different atom, we would make a different molecule. It wouldn't be water anymore. Same thing with removing atoms. So let's take this example here, which is a little tricky to think about. I'm going to blow this up a bit. Okay, so in this example what we're doing is we're taking lead and sulfur and we're reacting it to form lead sulfide. So in the top example we have 10 grams of lead, we've got 1.15 grams of sulfur. Conservation of mass says that we can't gain or lose mass there, right? So our final product that we get out, this is just the sum of masses for our 2 starting materials. So that follows the conservation of mass law. But then in the next example, if you look at it, we still have 10 grams of lead, but now we've got 3 grams of sulfur. Another way of thinking about this is compared to the one above it, we now have an extra 1.45 grams, right? Compared to the question above it where we had 1.55. The law of defined proportion says even though you have extra, it's not going to react, right? Because it's in a defined ratio. If you have extra, it's just going to be left over at the end. So this is unreacted. So really what we're doing is we're comparing this amount to that amount, and we're saying we've got an extra 1.45 grams. In this case, that's just considered excess reagent. All right, if we do the example of the bottom one, what we have here is 10 grams of lead that now has an extra 8 grams added to it, so now we have 18 grams of lead. Which means, again, we've got 8 grams of lead that's left over. It doesn't matter if you add extra. In this case, the sulfur is limiting the reaction and not the lead. So just because you add more lead doesn't mean you're going to get more product. You would have to add more lead and more sulfur in order to get more lead sulfide out of this reaction. And really, that's how they did a lot of this when they were doing initial studies on the ratio of atoms to one another, was they would actually react them, figure out the perfect amount needed, and then if you had excess, they would use that data in order to determine how many lead atoms were in there, or how many sulfur atoms were in there. All right. So now let's do a different example. This is one I like a lot. You can actually take water, let me do this arrow, and you can split water into hydrogen, which is H2, and hydrogen is a gas. And you can also get oxygen out, and you get half of an oxygen molecule out for every 1 molecule of water. So we'll do half O2, that's oxygen, and oxygen is a gas. This can be done with a catalyst. And this is a big deal right now. So one of the big pushes in order to make our country energy independent is maybe to look into the hydrogen economy, so creating hydrogen cars, hydrogen fuel cells for power stations and things like that. And we can actually make hydrogen from splitting water. It's just fairly energy intensive right now. So we're trying to figure out cheaper ways in order to do this. And if you look at our current setup that we use, it looks a little bit like this, where you have this big bulb of water on the top. And what you do is you apply a current to some electrodes. And these electrodes are down on the bottom, and we'll talk more about electrodes when we get to our battery section. But what ends up happening is you create those two gases, your hydrogen gas and your oxygen gas. But if you notice, the volume of oxygen gas there is half of the volume of that hydrogen gas, right? And so that's exactly where we get this ratio of 1 to 1/2, right? So we get half as much oxygen out as hydrogen out. And this is how we determine how reactions work a lot of times. So in this case, so when we split water, we produce hydrogen gas to oxygen gas. In a 2-to-1 ratio. There's actually a really cool scientist, I think he's at Harvard right now, that actually has this metallic thing that he calls an artificial leaf. And what he does is he sticks it into water, and if you shine sunlight on it, it will actually start bubbling the water, and those bubbles are hydrogen gas and oxygen gas, and he can collect them and use them as energy sources for developing nations. And so he's actually creating this artificial leaf that is about 100 times more efficient than an actual leaf at producing energy. And so there's a lot of scientists looking at similar ideas, and they're trying to figure out, again, using this really basic idea of splitting water into 2 parts hydrogen to 1 part oxygen. All right. Now let's talk a little bit about atomic theory. Atomic theory basically explains the inner working of atoms. And the atomic theory was developed by John Dalton. In 1803. And really what he did was he looked at all of the published scientific research at the time and tried to condense it down into a nice cohesive theory. to explain why atoms are the way they are. And specifically, the theory he developed was used to explain the law of conservation and law of defined proportion. So the laws were figured out quite a bit before the atomic theory came around. He was the first one to really sit down and try to explain how or why they were working the way they work. And there's 4 key parts to this. So the first part of his theory was one that we already know about, and that is that all matter is composed of atoms. Believe it or not, this was actually fairly controversial for a long time. People used to hold a really strong belief that your soul actually weighed something. And so they would weigh people before and after they died, and that was actually a science field for a while, which is weird to think about. It was usually just the fact that they were losing water weight. Your soul doesn't weigh anything. But all matter is composed of atoms, and all atoms have mass, right? So he was the first one to throw this theory out there. The second part is that all atoms of a given element are alike. And they are unique from atoms of different elements. I'm going to throw an asterisk in here too, because he wasn't entirely correct on this point. And one cool thing I like to explain to people is, has anybody heard of heavy water? Heavy water is a type of water, but it actually has a heavier isotope of hydrogen in it called a deuterium atom. It's still a hydrogen atom, but it's slightly different. And we'll talk about why it's different in the next chapter. But the cool thing is, with heavy water, if you freeze it, the ice cubes will actually sink in your drink glass. So he didn't know about these special types of isotopes when he was studying the atomic theory. He thought that all atoms and elements acted exactly the same. The reality is, it's not entirely true. Isotopes can behave differently. So we'll say he didn't know about isotopes. All right, the third part of his theory was that compounds form when atoms of different elements are combined in a fixed ratio. When atoms of different elements are combined in a fixed ratio. So this was his attempt to explain the law of defined proportions, that summary of observations, and he said that, well, that's because water, for example, is always H2O. It's never going to be H3O. So you need two hydrogen atoms to bond to one oxygen atom to create water. All right, the last one was that chemical reactions involve rearrangements of atoms. And he also said that atoms cannot be created or destroyed. So that was along those same lines. But again, I'm going to put in an asterisk here, because this was 1803. He didn't know about the atom bomb. He didn't know about any of that stuff. So this doesn't really include any nuclear chemistry. The reality is we can actually create some atoms and we can split other atoms apart. So if we look at our sun takes hydrogen atoms, smashes them together and forms helium atoms. We can take uranium, we can split it apart into different atoms. He just didn't know about this at the time. So his theory took into play all four of these parts, and it does a pretty good job of explaining most of what we see today. The tricky part was they knew about atoms, they knew about law of mass conservation, defined proportions, all of this stuff, but they just had this hodgepodge of atoms, and they didn't really know a good way of organizing it. But a lot of interesting things happened around this time, specifically from a Russian chemist, and his name was Dmitry Mendeleev. And what he did was he had this big pool of atoms that we knew about. We knew about hydrogen, we knew about oxygen, and he began studying all of the different elements out there. Specifically, he tried to organize them based on reactivity. So he tried to organize elements by their reactivity. So, for example, I've got this table down here, and I know it's kind of hard to see. But if we go through, I'm going to point out some unique ones here. We've got lithium right here. Lithium is a soft metal, low density, very reactive. And then we go down the list to beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and then we go to sodium down here. If we look at the definition, it's a soft metal, low density, very reactive. So it's got really, really similar properties to lithium. We can keep on going down the period or down this list and get to potassium. Potassium's a soft metal, low density, very reactive. So what he started noticing was that there were a lot of elements out there that had really, really similar reactivity. So what he did was he tried to organize these. And at the time, he only knew of 63 elements, and basically made a chart exactly like the one below where he tried to organize these 63 elements. And he noticed that, for example, there was a gap between lithium and neon of a certain number of elements. And in some cases, those gaps were incomplete. He was predicting that there should be something there, but there's not. And so he actually predicted the discovery of new elements. They were just gaps in his table. All right, so I want to show you guys kind of a cool video, and it specifically talks about lithium, sodium, potassium. And then if we look at our current periodic table, we can even keep on going down. And these are some of my favorite elements that are out there. This is from a British show.
Whether you've left school or you're still at school, you can appreciate the sheer fun, mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. Thank you very much. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes! That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There's one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, frankium. But for some reason they wouldn't let us have any of that. So, there you go. Today's lesson.
Never mixed alkali metals with water.
So basically they're showing exactly what Dmitry Mendeleev did. He would pull out all of these elements, see if they reacted in a similar way. And so, for example, he noticed that lithium, sodium, potassium, they all explode when you throw them in water. Same thing with rubidium and cesium. And you may notice, too, that oftentimes as you go up or down the periodic table, things become much, much more reactive. So on that side of the periodic table, as you go down, they become more reactive. And on the other side, they become more reactive, typically as you go up the periodic table. Yep. So that's a good question. So the potassium in your bananas is different than potassium metal. Potassium metal means that it doesn't have a charge. The potassium in your bananas is actually something called a cation. So it's not a true metal at that point, it's just an ion. Similar to saying that sodium chloride, or salt, that's very, very different than sodium as a metal, right? Sodium as a metal would explode in water. If we put salt into water, it's completely unreactive, it just dissolves. Yeah. All right, so let's take a break right now, and then we'll come back and talk a little bit more about the periodic table. So Dmitry Mendeleev, like I was saying, would go through all of the elements. He determined that after going through them, that there was this order to how they were laid out. So lithium was very similar to sodium. And he began organizing his table. You can actually pull up or look at his table in your textbook. This is an example of how he laid it out. But like I said, the really fascinating thing was that he had all these gaps in his table where he was predicting elements that weren't yet discovered. And then later on, those gaps got filled in, and they matched his predictions about what reactivity they should have. And so now we don't really deal with a table that looks like his. We deal with a table that looks more like this, right? So this is our standard periodic table. And if you look at the periodic table, it's organized so that each of these columns have very, very similar reactivity. So when we're looking at similar reactivity, we're looking up and down a column, not horizontally across the row. So in particular, what we call that is group number. So for example, we've got group 1, group 2, and so on, all the way across the periodic table. Those groups have very similar reactivity. We also have unique names for the groups, too. So you may have heard him say in that video that sodium and potassium are alkali metals. So if you look at the key down here, alkali metals are that blue color. The group next to it, group 2, are the alkaline earth metals. And then if you get to that fat middle section of the periodic table, that green portion, those are called transition metals. So again, they're all metals, but they're called transition metals. And then if you go over to the right-hand side, we've got a little light pink section called post-transition metals. And then we've got something that looks like a staircase right here. You guys see that? Those are called metalloids. They're things that are kind of in between metals and non-metals. And then in the yellow section, we've got nonmetals. These are the things that make up our DNA, our proteins, things like that. And then in the red, or kind of pink, depending on how it's showing up there, those are called halogens. We'll talk more about those too. And then noble gases are on the far right. Noble gases, like I said before, they're the things we see in those fluorescent signs and street lights and things like that. They don't like to be very reactive at all, so they're in their own unique column. Okay, so now let's take a closer look at some of the symbols that we see in the periodic table. And for example, I'm going to pull up Fe. And normally what we see is a number above it. We see a name, in some periodic tables at least. And then we see a number below it. So the question is, what does all of this mean? The top number is referred to as the atomic number. And we'll talk a little bit more about what this means when we get into the atom, but the atomic number refers to the number of protons that an atom has. Fe is just the element symbol. Iron is obviously the element name. And what do you guys think that bottom number is? Yeah, it's the mass of our atom. And so what we call this is atomic mass. And specifically, we've referred to this in AMU AMU stands for atomic mass unit. It's just how we weigh atoms or elements. And specifically, this is the average atomic mass. So like I said, hydrogen has isotopes. Some of those isotopes are heavier. So what we do is we average out all of the hydrogen in the universe and all of its isotopes, and we'd say this is the average atomic mass for hydrogen. So now we need to define what an AMU is. And that is our atomic mass unit. And basically what it is it defines the weight of an atom. So let's take our example with water that we talked about earlier. And with water we said we can take water, which is H2O. We can split it into hydrogen gas. Whoops. And oxygen gas. And the thing that they looked at was they looked at the hydrogen and oxygen and they compared the mass of each of these. And so in this case, what they found out was that oxygen's mass was 16 times greater than hydrogen's mass. So let's take a look at the periodic table. Hydrogen is H in the top right-hand corner. Its atomic mass unit is really close to 1. If we go over to oxygen, which is atomic number 8, the mass is really, really close to 16. So what they did was they would split things apart, determine the relative mass of each. One AMU is really, really close to the mass of a hydrogen atom. So this was used to determine relative mass for all elements. Which is pretty handy. You would anticipate, well, we're only getting half of an oxygen out. It should weigh less, but in this case, oxygen atoms just weigh a lot more than hydrogen atoms. So even though we're producing half as much oxygen as hydrogen, that half amount is 16 times heavier than the full amount of hydrogen. All right. There's also a unique standard too. So hydrogen isn't quite the standard that we use. The standard that we use is called carbon-12. Specifically, what carbon-12 means is that it's a carbon with a specific number of neutrons. And specifically, the standard says that one carbon-12 atom equals 12 AMU, or atomic mass units. So carbon-12 weighs exactly 12 AMU, so 12.0000000. It's exactly 12. The interesting thing is, if we look at the periodic table, the atomic mass listed on the periodic table is 12.011, which means we've got some other types of carbon out there. So let's talk about that. We've got 4 main isotopes of carbon. And what that means is it just has a different number of neutrons. So the first one we mentioned was carbon-12. Then we have carbon-13. And then we have carbon-14. So the difference between carbon-12 and carbon-13 is that carbon-13 has an extra neutron. And we'll talk about neutrons and protons next week, but it's a particle in the atom itself that gives it a little bit extra weight. And same with carbon-14. Carbon-14 has 2 extra neutrons, so it's even heavier. And if we go out in the environment, we can actually detect carbon-12, carbon-13, carbon-14. Carbon-12 makes up approximately 99% of all carbon. Carbon-13 makes up approximately 1%. And then carbon-14 makes up 1 part per trillion. What we do is we say, all right, if we take the average mass of all carbon atoms on our planet or in the universe, it's going to be equal to that 12.011. And this is the value we see listed on the periodic table. The value listed on the periodic table is just looking at all different types of carbon out there. And it's slightly above 12 due to those heavier isotopes of carbon on the periodic table. So it's kind of an interesting thing to think about. We can also go through and we can relate atomic mass units to a gram value. So now that we've got our SI units figured out, we can say that 1 AMU equals 1.6605 times 10 to the negative 24th grams. So that's our other standard too, now that we have our scientific SI units that we work with, and those are always going to be in grams. Let's do a quick refresher math problem just so we can practice doing unit conversions. I'm going to use my Batman example. So how much does Batman weigh in AMU, or atomic mass units? And recall his weight is 95 kilograms. So now we have to figure out the overall mass in AMU rather than in kilograms. So how would we go about doing this math problem? What do you guys think? kilograms to grams. Yeah, I think that's a great idea. So we'd say, all right, 95 kilograms. We want to cancel out kilograms, so that goes on the bottom. Grams go on the top, and then what number goes where? A 1,000, does that go on the top or bottom? The top, right? Because grams are the smaller unit. So in this case, 1,000 grams go on top. Cancel out kilograms and kilograms. Put one on the bottom if we'd like. And then we need to cancel out grams. So we'll put grams on the bottom. And we want our final answer to be an AMU. So if we do this, we cancel out grams and grams and we'd be left with AMU, but what number goes where? So remember, we're saying 1.6605 grams would be equal to 1 AMU. So you want to make sure that the top and the bottom are equal. That way they cancel out. So we would say 1.6, let me slide this over, 6605 times 10 to the negative 24th grams for every 1 AMU. Cancel out grams. Now we can do our math, but we also need to keep track of Sig Figs. So I'll do this on my calculator. You guys are welcome to double check me because I'm occasionally wrong. So I'm getting, a value of 5.721168,323 times 10 to the 28th. AMU. Is that our correct answer? Or do we need to do anything else with it? Sig Figs, right? So let's go back and look at this initial one. We had 2 Sig Figs here. This is defined, so it doesn't matter. And then we've got 5 Sig Figs over here. So our final answer should only have how many Sig Figs? Just 2, right? Because that's got the least number there. So we want to look at this. So what we'll do is just chop off the rest of that number. We don't have to worry about rounding because it's lower than 5. So our final answer would be 5.7 times 10 to the 28th AMU. So we can actually use AMU now as a conversion factor. And we're going to be using this a little bit when we get into our section on stoichiometry, which is basically just a fancy term for math with chemistry. All right, so I think we've got some time to do some practice questions. Yep. 10 to the 28th. So because this negative 24 is on the bottom, when you go through and do all the math, it actually turns that exponent into a positive number. So if you want, we can talk after class and check it out on your calculator and make sure it's working all right. But yeah, it should be a very, very large number because an AMU is a tiny, tiny amount of mass. All right, so let's do some practice questions. The term atom comes from the Greek word atomos, which means what? We didn't really learn the Greek term, but we can figure this one out. Maybe, so we can't see atoms easily, but I showed you guys that IBM video where we can see some of them now. But what's special about an atom for the most part? Yeah, they're really small, and then can we cut them very easily? No. So Dalton was one of the first people that said atoms cannot easily be cut unless we're getting into strange nuclear chemistry or something like that. All right. The fact that 4 grams of hydrogen reacts with 32 grams of oxygen to give 36 grams of water is an illustration of what law? Yeah, exactly. So if we're putting in 4 grams, reacting it with 32 grams of something else, you add them together, you're going to get 36 grams. It's saying that we can't create or destroy mass in this reaction. All right, so the tarnish on silverware is primarily silver sulfide, which is always formed in a 2-to-1 ratio of silver to sulfur. This is an example of what principle? Yeah, law of definite proportion. So it's saying that you're always going to have that 2-to-1 ratio because that is what makes up silver sulfide, or that tarnish on there. All right, let's do the next one. Carbon and oxygen can react to form carbon monoxide or carbon dioxide depending on the amount of oxygen available. This illustrates what law? Kind of. This is actually referred to as the law of multiple proportions. So you remember when I was talking about lead and sulfur? It's basically saying anytime you take 2 elements together, it doesn't matter if you had extra of one, it has to be in that defined proportion ratio. So in this case, it's talking about law of multiple proportions. I don't like using that name too much because it confuses people with law of definite proportions. So just remember, though, that you have to have that set ratio, otherwise you'll just be left with excess leftover starting materials. All right. This is a picture of Dmitri Mendeleev. He looks like a wizard, I think. He arranged the elements in his early periodic table primarily according to what? Physical properties, chemical properties, mass, appearance, or abundance? Yeah, chemical properties. He was seeing how they reacted. So just like that video I showed you, those all had really similar explosive reactivity. He did that same thing. He didn't do similar physical properties because, as you guys saw in the periodic table, a huge portion of them are metals, but that doesn't mean that they have the same reactivity. All right. I like this next one. Early flash bulbs were composed of magnesium, which when ignited by an electric current would explode to form magnesium oxide and give off a bright flash of light. The reaction is described here. Got 24 grams of magnesium. That's weird. I wonder why it says magnesium oxide on the bottom. I'm not sure what these things are referring to down there. And then the next question says, the question that it's referring to says, when 6 grams of magnesium reacts with 12 grams of oxygen, how much magnesium oxide will be formed? So let's scratch out this bottom part. I think that's just a typo. So it's saying instead of 24, what if we go from 24 to 6? And then what if we go from 16 to 12? So we've cut the magnesium by a quarter. We've cut the oxygen by less than a quarter. So which one did we cut the most of? Yeah, the magnesium. We cut out a lot of the magnesium. So in this case, it's saying, all right, we cut out the magnesium. We're going to react it with the oxygen. And how much oxygen do we need for every gram of magnesium? This one's a little tricky. So it's saying we have 6 grams of magnesium. And it's saying we need based on our bounced reaction above. 16 grams of oxygen for every 24 grams of magnesium, right? That was our ratio in our balanced equation without any leftover. So now let's do the math on this. Wait a second, did I screw something up here? So 6 grams of magnesium. Okay, so this gives us four grams of oxygen. Sorry, I typed it in wrong in my calculator, right? So now we've got 6 grams of magnesium reacting with 4 grams of oxygen. What will our final mass be? Yeah, it'd be C. So 6 grams of magnesium plus 4 grams of oxygen equal 10 grams of product. This one is a little confusing because it's kind of a wordplay problem, but it's trying to combine a lot of these ideas together. So what happens to the excess oxygen that we had in there? We only needed 4 grams and we have 12. Yeah, it's just left over. So if we look at this, we get 10 grams of product and then 8 grams of leftover oxygen. We only needed 4 grams for the reaction to occur in that correct ratio. So it's a little bit tricky for that one. All right, so remember before next Monday comes in, you need to have your typed lab report. Try to include all this data in your lab notebook as well, but the only thing you're handing in to me is your typed lab report. If you guys have questions on it, email me, and then also work on your homework and have that to hand in too. So I'll have 2 stacks on Monday of assignments to be collected. All right, have a good weekend, you guys.